we will be using the idea of the inverse function to come up with the derivatives of the inverse functions of all the functions we have already found the derivatives for. So we'll essentially double our store of differentiation facts by using this idea of inverse function. And in pre-calculus, you've learned to notate the inverse function as f negative 1 of x, whereas f without the negative 1 is considered the function itself. So y is the inverse function of f if and only if x is f of y. Notice the negative 1 here and the lack of the negative 1 here. If the forward function is f, the inverse function is f to the negative 1. And we have a quicker way of writing that, which is y is the inverse function of f if and only if x is the forward function of y. And this is how we understand that. This is what we expect from the inverse function definition. That is, y equals the inverse function of x. Well, if we take x from this side, which is f of y, what this says is that f inverse of x, where x is f of y, and we expect the function and the inverse function to undo each other and simply leave you with y, and we end up with y equals y. So that's the idea of the inverse function. The inverse function is the function that undoes the original function and leaves us with the argument itself. And it works the other way around. Right? We can start with x equals f of y and replace y with what y is according to this definition, which is f inverse of x. And f and f inverse undo one another and leave you just with the argument, and that gives us x equals x. That's essentially what we mean by the inverse function, is that the inverse function undoes the forward function, and the forward function undoes the inverse function. And you end up, what you start out with before you start the operations is what you end up with when you finish taking the inverse of the function, and vice versa. You start with x and you end up with x. The function undoes the inverse function. So here's our thought, and that is that we can possibly use the inverse function to help us come up with the derivatives of the inverse functions for all the functions we already know. We know a bunch of functions already. We know e to the x, a to the x, all the trig functions, and soon we will know the hyperbolic trig functions. But we do not know the derivatives of the inverses of all those as of yet. And the inverse functions of e to the x is ln of x, so we'll find the derivative of ln of x. We'll find the derivative of the general log, because it's the inverse function of a to the x. And then we'll find the derivatives of all the inverse trig functions using the trig function derivatives we already know, and the same thing with the hyperbolic trig functions. So this is a fairly important concept for the half of the derivatives that we don't know already. Here's one of those proofs that you might expect will be on the exam on the chapter on differentiation, and that is the fact that the derivative of the general exponential function is equal to the function you started with times the natural log of the base. We already know from section 3.1 in the text how we came about believing that the derivative of e to the x is e to the x. We manufactured a particular exponential derivative that would give us that result. Then the question is, what about if it isn't e? What if it's 2? What if it's 3? What if it's 10? What is the derivative of an exponential with base a to the x? And the answer is, it's just like the derivative of e to the x looks like e to the x, the derivative of a to the x looks a whole lot like a to the x, except there is this little fudge factor there, which is multiplication by some constant. The only case in which the constant is 1 is when it is e, and that would make sense, because if this was e to the x and this was e to the x, this would be the natural log of e, which is 1. So let's see how this proof develops. It's actually based upon a little bit of pre-calculus. The main trick here is you need to write a to the x in a form that allows us to differentiate it. And whereas we don't know how to differentiate a to the x, we do know how to differentiate e to the x or e to something using the chain rule. So if we rewrite a to the x as e to the ln of a to the x, e to the ln of x, you should realize that that is a to the x. So we've transformed this into an e to the a base e derivative. So a to the x, if we use the properties of exponents or of logs and bring the x out as a multiplier, then we can differentiate this using the chain rule. So the derivative of a to the x, differentiated to the right hand side, is derivative of e to the thing is e to the thing times the derivative of the thing, and the thing in this case is x ln of a. The derivative of a constant times x is just the constant. In this case, the constant is ln of x. So that leaves us with the derivative of a to the x being e to the x ln of a times the natural log of a. And then the only thing left to do is to show that this thing can just be replaced, this e x ln of a can be replaced with a to the x. And of course it is just a to the x, because you can see now in step 2 it is a to the x. Therefore the derivative of a to the x is a to the x ln of a, QED.